In Unit 11, we're going to look at exponential and log functions. So the first thing we're going to do is we're going to look at exponential functions. And to kind of understand exponential functions, we're going to start by looking at their graphs. Generally speaking, whenever we have an exponential function, it's in the form y equals a times b to the x. And a is going to represent this initial amount, so whatever we're starting with. And b is going to be the growth or decay rate. So this is going to be growth or decay rate. But b is considered the base, and the reason why this is considered an exponential function is because the variable x is now the exponent. Typically, x is not an exponent. It might be like x squared or x to the third, but in this case, x is the exponent. So that's why they're called exponential functions. So looking at the graphs, we have two different types. We have an exponential growth and then an exponential decay. So this graph here is a growth, exponential growth, where this one is going to be a decay. And the difference is, if you think about growing, you're going up as you move left to right. Decay, you're decreasing as you move left to right. The difference in the equation is going to be whenever I have y equals a times b to the x. Here, for growth, b has to be a number bigger than 1. So if it's growing, the growth rate will be bigger than 1. If it's decaying, then I'll have my equation a times b to the x. But that b value is going to be a fraction. So it's going to be something between 0 and 1. So it'll be a fraction or a decimal. It won't be negative. It'll just be some positive number between 0 and 1. And then the other thing here to look at is the asymptotes. So an asymptote is whenever you have your graph is reaching a point, but it's not actually crossing a point. So in both cases here, the asymptote is going to be the horizontal line at y equals 0. So this here and this here are going to be your asymptotes, because if you look, both graphs get really, really close to that line, but they're not actually going to ever cross it. So both of these have asymptotes at y equals 0. So really these graphs are, you can't really see it, but they're getting really, really close to that, but they won't actually ever cross it. So then the next thing we're going to look at is just actually coming up with a graph. So for this example, we're just going to graph this function f of x equals 10 to the x. So this is just a common exponential function. Now notice that all exponential functions or all exponential graphs are functions because they pass the vertical line test. You can draw any vertical line through these and they'll still be functions. So I can write them using y, or I can write them using f of x. It doesn't really matter. So if I want to graph this, basically what I'm going to do is just create an xy table. So this is in standard form. This is like a parent function where 10 is the base. So I'm going to get some negative points. So I'll start at -3, -2, 1, 0, 1. And really, if I stop at 2, that's going to be enough because that's going to go off the graph. So I just pick some points and I'm going to plug them into this equation. So really this becomes 10 to the -3. And you can put that right into a calculator and you're going to get 0.001. Really what this is saying is 1 over 10 to the 3, because whenever you have a negative exponent, it goes down to the denominator. This one is 10 to the -2, which is really 1 over 10 squared. So it's 1 over 100, which would be 0.01. But again, you can just put this right into a calculator, 10 to the -2 right into a calculator. This one we have 10 to the -1, so we get 0.1. This one we raise 10 to the 0, we get 1. 10 to the 1, we get 10. And 10 squared, we get 100. So you can see this grows really quickly. It gets really big fast. So when I go to plot these points, So -3, I mean, these are going to be so close to 0 that you're not going to really be able to see much of a difference. And then once you get to the positive numbers, you start to see this really grow. So 2 is going to be way up. So then when I go to connect it, I know that since this is an exponential function, I know that it's going to have an asymptote. And whatever this number is at the end, so in this case it's really a +0, that's going to be my asymptote. So I know my graph is going to basically grow, and it'll come down, and it'll get really, really close to the x-axis, but not actually ever cross it. So this is going to be f of x equals 10 to the x. And again, there is a horizontal asymptote here at y equals 0. And the reason why we would never cross this line is because there's no way for you to raise or to have a negative exponent or a positive exponent and get negative numbers. So even plugging in negatives, you're just going to get closer to 0. You're not going to actually ever get a negative, so it's never going to cross over this. So this is your basic graph. 10 to the x is going to be a popular one, and we'll see why later on. But for right now, it's just basically anytime you have to graph an exponential function, just plug in some points. The next thing that we want to look at, though, is, well, what happens if it's not just a basic parent function? So what if we want to translate? So now we're kind of connecting in our old unit with this unit. So the first one here, if this is kind of a standard form of a translate, an exponential function that's been translated. So if you notice, we still have a parent function here. Our parent function is going to be that standard form, the basic without the shift. And our parent functions are never going to be the same functions, but they're going to be y equals a times b to the x. A and b are going to be different numbers. So in that last example I had, a was 1 and b was 10 because it was y equals 10 to the x. Since there was no number in front of 10, it was just a 1. So just know that that's going to change. The parent functions aren't the same every time because a and b are going to change. But then the translation part of this, back from last unit, if you think about your HIVO, if it's in the inside, it's going to be a horizontal. So this H is in the inside, so that tells me it's going to be a horizontal movement. So it's always going to be, H is going to be your horizontal, but you're going to do opposite. So if it's a negative H, really what that tells me is that I'm going to be moving right H according to this. And then the K is on the outside, so you're going to do what makes sense. So since it's plus K, it means you're going to be moving up K. So your translation is always going to be decided by H and K. If H is positive, you move right. If K is positive, you move up. And just kind of remember your acronym there. Another important thing, too, is this number at the end, that K value, is always going to be the asymptote. So the graph that I just graphed had a +0 at the end. So that's why the asymptote was on the x-axis. So this is always going to also be the asymptote. Because the standard parent function is always going to have an asymptote of y equals 0, but once you start to shift it, the asymptote's going to change to match that shift. So the asymptote here is y equals k, whatever that k is. So if we look at this first example, when we go to graph this, the first thing we want to do is figure out the parent function. So the parent function is what we're going to start with, and then we'll graph that, and then we'll do the shift. It's easier to start by graphing the parent function because it's easier to calculate. So in this case, the parent function is going to be 3 times 2 to the x. So again, we're ignoring the shift. So we're just going to make an xy table for that. So we'll go from like -2 to 2. That'll give us a good set of points. So basically, I just plug in -2 into this. Just use your calculator to do that. We get 0.75. Plug in -1, we get 1.5. 0, we get 3. 1, we get 6. And 2, we get 12. So we just plug those in. And now I'm going to go ahead and graph that. So I have negative 2.75, negative 1, 1.5, 0, 3, 1, 6, 2, 12. And again, we know that the parent function is going to have an asymptote of y equals 0, so basically this is not going to cross the x-axis. So it's going to flatten out and then just get steeper and steeper. So this is our parent function. And now what we're going to do is we're going to figure out the translation. So the translation for this, if you think about HIVO, so the horizontal is the inside. So that's going to tell me it's positive, so we do the opposite. So we're going to go left 1. And then the VO, vertical outside, we're going to go up 5. So we're going to take each of those key points and shift them. So we're going to go with each point up 1, or left 1, over, up 5. So left 1, up 5. And then we can connect them. And remember, where the graph started to flatten out here, it means it's going to start to flatten out in that same spot when we shift it. So again, remember too, we said that the asymptote is whatever that vertical shift is. So the asymptote is always this number here at the end. So y equals 5 is the asymptote, which if you look at my graph, that makes perfect sense. And I'm going to graph only this final asymptote, not the original, just because I want to show you this and I don't want it to be confusing. So this is the y equals 5. That's the asymptote of my actual graph. So my actual graph, y equals 3 times 2 to the x plus 1 plus 5. And then the other thing, so it said be sure to state the asymptote, the intercepts, domain, and range. So there's my graph. So it's been shifted, same shape, it just moved around. The asymptote then shifts up because it will never cross y equals 5. And then the y-intercept is always going to be that initial value. So the y-intercept is where this graph is crossing the y-axis. So basically when x equals 0, so the y-intercept, let x equals 0, and we'll just plug in. So y equals 3 times 2 to the x, so it's going to be 0 in for x plus 5. And then y equals 3 times 2 plus 5, so y equals 11. So the y-intercept is going to be 0, 11. Now, for these other parent functions, the y-intercept's always that initial value, which is always that a value. But since this has a shift on it, that's why it changes. So you can't just use 3 as the initial value. You actually have to plug in 0. So just plug in 0 for x, and that'll get you the y-intercept. And then the other piece is going to be to find the domain and range, just to kind of review that. So domain, as you move left to right, you're going to include all real numbers because there's arrows. This is going to keep going left, and it'll keep gradually going right. So it'll be all real numbers, so negative infinity to positive infinity. And then for the range, the y value, since there's this asymptote here at y equals 5, you'll never go below y equals 5. It'll always be getting really, really close to 5, but not actually touching it, and up to positive infinity. So I'm going to use a soft bracket around 5, and it's going to go up to positive infinity. Soft bracket, round bracket, because I'm not including 5. I'm just getting really close to it. So really the range will always be whatever the asymptote is, up to infinity. So let's look at just one more example. This next example is an exponential decay example. The reason why I know that is because inside here the b value is 1/2, It does have a shift on it. It also looks like it's been reflected. So that tells me, because there's this negative, remember that's a vertical flip. So that tells me that this is not going to be going upward. It'll be basically flipped over the x-axis. So it'll look a little bit different. So let's go ahead and start with the parent function for this. So when we do the parent function, we're going to include that negative so we don't have to worry about flipping it. So we'll just make our parent function -2 times 1/2 raised to the x. So the only thing we won't ever include in our parent function is going to be the shift. So then we'll come up with our table. So if we just do -2 to 2, that'll kind of give us a nice symmetric picture here. Oops. And I put in these numbers for x in my calculator. I get out -8, -4, -2, -1, -0.5. And again, we're seeing that this graph is in the negative numbers only because that negative outside of 2, it was flipped. So now when I go to graph this, I have -2, -8, -1, -4, 0, -2, 1, -1, 2, -0.5. So my asymptote is still going to be y = 0, but it's coming from the other direction this time. So it'll get really, really close to y = 0, but won't actually cross it. So again, picture this as a flip, because typically a decay graph is going to go down like this, but this graph's been flipped because of that -2. So next thing is to look at the translation. So we're going to take each of the key points and move them. So we look at hypo. This is -3. That's going to be our horizontal. So negative really means you go to the right. And then the +1 tells me to go up 1 because that's the vertical outside. So you're going to take each of these points, go right 3, up 1. And then again, when you go to connect these, you should see that it's going to start leveling off. And it's basically your asymptote's just getting shifted whatever that vertical shift is. So since I moved everything up 1, that just means that my asymptote's also going up 1. So my asymptote, instead of being at y = 0, it's going to be at y = 1. So the asymptote is at y = 1, which again, you could have just looked at the end. The Y-intercept is the next thing. So we're going to let x = 0, and we want to plug into the entire original. So remember, you can't just use that a value unless it's a parent function. So I have to plug into the original, which means it's going to change. So then we go ahead and calculate that. We get -15. So my y-intercept is 0, -15. And then the last thing is to look at the domain and range for this. So domain and range of the blue graph here. Domain, it's going to keep going towards positive numbers. It's going to keep going towards the negative x values, because it's going to keep eventually getting wider. So -infinity to +infinity. Range for this, it's going to start up or down at -infinity. And it's going to stop once I get to this asymptote. It won't ever cross y = 1, but it also won't ever touch it. So that just means it'll get close to it. I use a soft bracket. So that's really it. So it's really just figuring out the parent function, using the parent function to start. Remember, the asymptote's always a number at the end. And if you're looking at the parent function, the y-intercept is always this number in front. But if you're looking at a shift, then that's not the case. So you look at plugging in x = 0 to find the y-intercept, and then your shifts, you use hypo. Horizontal inside, vertical outside. Always do the opposite for horizontal, keep the same for vertical.